Okay. Excuse me. So first of all, exam 2 is Monday. The topics are going to be up through the kinetics of rolling down a ramp. No, no pulleys with mass. So we're going to do that today, pulleys with mass, but I'm not going to give you an assignment over the weekend, so we'll just put that off till next time. Okay, so almost everything in kinetics of rigid bodies, but not the stuff that we're starting today and doing today. And the Pinewood Derby stuff, that is not going to be on the test. That's just sort of an example, but you should be able to do problems of just wheels or balls or rings or whatever rolling down a ramp, okay? Anybody have any questions about the test? Yeah.
It's the same format for the test, right? Like same number of questions.
Yeah, roughly. Yeah, same format. It's just going to be problems, no questions or anything. We'll put that stuff off for the quizzes. Yeah, those short answer questions will just be for quizzes. And like always on my tests, if you know how to do all the daily problems and understand them, then you'll do great on the test. Like really you should know going into the test in most cases, like how you're going to do on it, just based on how, well you've covered the problems and how well you understand them if you pull one up, Any other? Yes.
What moments of inertia should we memorize?
None. I will give you all that. Really, just about any formula you can think of, I'll give you if you need it. Yep. Any other questions about the test? Okay. Any homework questions before I go back to what we were doing last time? Okay, so we're in the middle of that Pinewood Derby question, or pretty close to the end, actually. And the setup for this problem was we have an incline with an angle of theta. We have a body of the car with a mass big M. We're using a coordinate system like this. There are 4 wheels, each with mass, lowercase m. And last time we had just gotten through all the kinetics, and we had the following 4 equations. So the first one said 4rx plus big M g sine theta is equal to big M A. The second one says negative Rx minus FF plus little mg sine theta is equal to little ma. The third one says negative RFF, that's the radius of the wheel, is equal to CM R squared alpha. Anyone remember what that C is? So remember we assumed that each wheel has a moment of inertia about its center that's equal to CM R squared. Okay, so that's our way of saying, like, we're not going to specify exactly what the shape of that wheel is, but most round things have a moment of inertia of this form, you know, that C just changes, you know, it's 1/2 for a disk, 2/5 for a sphere, 1 for a infinitesimally thin ring. And so that's what that is. It's a stand-in for the moment of inertia. And then the last one is A is equal to negative alpha R. Okay, so these are our 4 equations, and now we just have to solve these. We're trying to come up with an expression for the acceleration. That's really all we care about, is the bigger the acceleration is of this Pinewood Derby car, the faster it'll get down the ramp. So we want to substitute, I'll use equation 4 to substitute that alpha is equal to negative A over R. And then I'll combine 3 and 4. So we have negative RFF is equal to negative CM R squared. So I'm substituting this in, so it's going to cancel one of those R's, and we just get this. And then we can cancel those R's, cancel the negatives, and we come up with FF is equal to CMA. Okay? So let's call this, so now you can think of, now we have a system of 3 equations for 3 variables, 1, 2, and let's call this 3b. I don't know. Let's not do that. But so I'll call that star now. Now we're going to substitute star into 2. So we have negative Rx minus FF, so minus CMA, plus little mg sine theta is equal to MA, little ma. I'll call that equation 2 star. And then the last one, I'm going to substitute 1 into 2. So 1 becomes, so So let's see, we got 4rx plus big mg sine theta is equal to big MA. And so we'll go 4rx is equal to MA minus, these are both big M's, MA minus mg sine theta. Then we'll divide by 4, and we get Rx is equal to m over 4a minus m over 4g sine theta. So you can see, if you remember, I said at the beginning that this problem is equivalent to putting all of the mass of the body of the car at the axles of the wheels. And so this is equivalent to just taking one of those wheels with a quarter of the mass at the axles. And now you can see that developing out of how we did it. Even though we didn't make that assumption at first, that's what we're getting. So now we'll plug this in for Rx into equation 2. So we have negative all of this stuff. Minus FF, which I guess I'm going to substitute in equation star. So I'll put that in here too. Oh yeah, okay, well let's not, okay. So this is actually equation 1 and equation double star that we're doing here. So we got the negative Rx minus CMA plus, that's a little m. Be sure you're getting these m's straight or none of this will make any sense. Plus little mg sine theta is equal to MA. And so now we'll get all the A's on one side, and I'm going to get all the A's over on the right, but I'm going to write it as if they're on the left, you know, just switching sides. So we have M times the quantity 1 plus C. So all I'm doing is moving this term here over times A plus big M over 4 plus okay. So plus big M over 4 times A is equal to big M over 4 plus M quantity times G sine theta. So we have, I guess I'll write this as M times 1 plus C plus M over 4. And I am going to write this whole thing as a fraction. So 4 of these plus this all over 4 times A. I'm going to do the same thing on this side. So we have big M plus 4 little m all over 4 times g sine theta cancel the 4's, and you get that A is equal to big M plus 4 little m all over 4m times the quantity 1 plus, come back, times the quantity 1 plus c plus big M times g sine theta. I'm going to rearrange these so you can tell, so you can sort of see the similarity in form. Okay, so if those wheels have 0 moment of inertia, what's the C value? 0. Yeah. Yeah. Yeah, 1 is bad. 1 is the ring. That's getting that's as much as you can get for a moment of inertia and still have a radius of r. So if that thing has no moment of inertia, C is 0. And notice that in that case, this fraction reduces to 1. And what you get for the acceleration is g sine theta, which is what we got for the frictionless block just sliding. Okay? So it's equivalent to sliding if those wheels don't have any moment of inertia. Okay, so like when you did physics labs with those carts that are designed to act like a frictionless thing that's sliding, remember those labs? Those wheels are really small, really light compared to the body. It has the effect of being close to 0 moment of inertia. And so what you get is something that acts like it's just sliding down the ramp with no friction. Okay? As that thing gets bigger, you get a bigger difference between these two things, and the acceleration starts to be less. Okay? And the biggest it can be basically is 1, so then you get a big difference. Well, say that the moments of inertia of the wheels are fixed. Say you can't do anything about that. That's how the Pinewood Derby works, is like they give you the wheels, you know. Then what could you do to make the acceleration as big as possible? Okay, remember that for a thing sliding down the ramp, or a thing with 0 moment of inertia on the wheels, the mass of the body has no effect at all. But notice if you do have moment of inertia of the wheels, you can get close to, you can increase the acceleration by increasing the mass of the body. Okay? So basically by overwhelming the moment of inertia of the wheels with this. Like if the mass of if that C value is 1 even, if it's something, and say this little m is 5 grams, okay? Well, you can overwhelm that by making the mass of the car body 100 kilograms or something, Then this equation barely notices that there are any wheels there, And so that's why the Pinewood Derby says, so that's why if you had a frictionless thing sliding down, mass wouldn't have any effect on anything. But when those wheels are given to you and you can't do anything about them, you have to put a limit on the mass of the body. Otherwise, it would just come down to who had the most massive thing on top of the wheels, And so, the reason we're all really here is just to learn how to cheat at Pinewood Derby. And so the answer to how to cheat at the Pinewood Derby is they give you wheels that have a cross section like this. Okay? And so what you want to do is you don't want to do enough that you make it obvious, but there's a lot of moment of inertia in these two, like the two lips on the outside. So you just want to sand these down so they can't see it, you know? And that has a significant effect on the moment of inertia of those wheels, which lowers this C value. And since everybody's big M is the same because everybody is trying, well, actually, if you do this, you can very slightly even increase your M value because there's just a fixed mass for the whole thing. And so there you go. That's an unfair advantage. They'll never know that you did it. You're still using their wheels, but the part that you sanded off is like tucked underneath, and they're stupid. Stupid idiots.
I don't think they'd expect someone to know that much about
Well, I'm sure, I guarantee if you spend 15 minutes searching, there are people telling you to do this. I guarantee that. You wouldn't believe how much energy and thought people have put into Pinewood Derby racing. Hey, this is funny actually, because a good friend of mine does this. You know, he was always like a Scouts leader. And at the LTD Brewery in downtown Hopkins, like every 6 months or something, they bring the Pinewood Derby track to this brewery, and people bring their cars, and it's like adult Pinewood Derby racing.
That is awesome.
Yeah, it's pretty awesome. And so I think you guys should do this and try to cheat my friend is really what you should do.
Have the Scouts on it.
Yeah, right.
It's a brewery. There's
No honor among thieves.
They don't care.
Question?
Would reducing the number of wheels also?
That's a really good question. And yes, that is perfectly legal even. You know, you can't reduce it down to 2 because it won't stay up. But people put one of the 4 wheels shifted up a little bit so that it only rolls on 3 wheels. And then, yes, you have the effect of reducing the total moment of inertia that you're spinning up. And it makes a big difference. And that's totally legal. But it takes pretty good engineering to make it like so that it rolls well on 3 wheels and this other one. I mean, you just have to be pretty precise with your building, you know?
Well, that's what we're here for.
Yeah, right. Any other questions about this? Okay.
You never won.
We never won. Let's see that. What was the best we did? It was a pretty big troop. And I think one year we got like 5th or something, maybe out of 25 or 30 or something like that. The one with I wish I would have started working on the 3D printed one a week earlier. I pretty much did it all like the day before. And then I didn't make the channels quite big enough for the nails, so things got a little messed up. But if I would have had another crack at it, I'll bet I could have gotten that one close to winning. Although I never tried lifting up the wheels, so anyone who lifted up the wheels, lifted up one wheel had a big advantage over what I always did. I think people, in talking to like other dads and stuff, I think everyone was kind of like iffy on like considered that sort of a gray area, like you can do it, but yeah, it sort of violates the spirit of the thing, you know?
Doesn't really touch.
Yeah. It definitely violates it less than doing this. Yeah. Well, also, you know what else? They give you So one of the things you can buy, I mean, you can go to hardware stores that support Pinewood Derby and they have all this expensive stuff for doing well. And one of the things is like a wheel, it's to make the wheels round, you know? Like, okay, basically they advertise that like, oh yeah, these wheels are slightly out around and that's gonna mess up your, and I'm just like, I really don't think it's that the wheels aren't round. I really think what it is in making them round, you're shaving, yeah, you're shaving off a little bit of this and a little bit of this. And those are the farthest away from the axis of rotation. And so you're reducing the moment of inertia of your wheels, you know? Okay, so now let's talk about the pulley. I like this one. So pulleys with size and mass. Okay, so I'm going to just set up a simple example. I think I'm going to just do this one with numbers instead of coming up with a formula like this. So I'm going to start with a base problem like this. Let's say we have a pulley attached to the ceiling. And let's say there's a 1 kilogram and a 2 kilogram mass. And so we're going to start out with just a massless pulley. You saw problems like this in Physics 1. I guess we did problems like this in particle kinetics too. We did 1 or 2 problems like this. So let's figure out what kind of acceleration you have if there's no mass in this pulley. And for all of this, we're assuming no friction, although friction is the easier thing to add in. I mean, you would just figure out the force of friction and just include it in there. Okay, so what's this going to do? Just orient yourself. You have the heavier thing on the left side. So the 1 kilogram is going to accelerate up. The 2 kilogram is going to accelerate down. To figure out the amount, so free body diagram of the 2 kilogram is 19.62, and then a cable tension like this. Free body diagram of the 1 kilogram is 9.81 down. Okay, and now what's the cable tension up? It's massless. Just T, yeah. But I'm pointing this out because that is going to change once this thing has mass. The fact that cable tension is the same all the way along its length depends on the fact that this is frictionless and massless, okay? So we're going to have to change that assumption in the next step. But okay, so Newton's second law, let's just I'll do the full thing. So for the 2 kilogram, Newton's second law says 0t plus 0 negative 19.62 is equal to the mass of 2. And then what do we know about that acceleration? We don't have to know which way it's going to accelerate. All we have to know is that it's going to be accelerating up or down. But since I'm going to sort of take a little shortcut, since I know that the 2 is going to accelerate down, I'm going to call this 0 negative a. And then Newton's second law for the 1 kilogram says 0t plus 0, negative 9.81 is equal to 1 times, and this one is going to be 0, positive A, if that cable doesn't stretch, you know. And so we have T minus 19.62 is equal to negative 2A, and we have, I'm going to subtract the y equation here, so this is going to be minus T plus 9.81 is equal to negative A. And then add the two equations. The t's cancel. You get negative 9.81 is equal to negative 3A. And so A is equal to, I think that's 3.27. Yeah, 3.27 meters per second squared. Okay, so that's if it's massless. What do you expect is going to happen to that acceleration as we add moment of inertia to this pulley? Yeah. Yeah, the acceleration is going to decrease until that thing is so massive that it just barely accelerates at all. Okay, so now let's say, what are we going to call this moment of inertia? Let's say we'll make the, so now the pulley is going to have size and mass. So let's say that the radius is, that's an okay size for a pulley, right? A diameter. So let's say the radius is 5 centimeters. The mass, what do we want to make the mass? 0.2 kilograms. And we'll just approximate this as a disk. So the moment of inertia about the center is going to be 1/2 times 0.2 times 0.05 squared. So 2.5 times 10 to the minus 4th kilogram meters squared. Okay, so now I'm going to start with a free body diagram of the 2 kilogram. So we have a force down of 19.62. We have a cable tension up of, this time I have to call that, you know, we're going to have to make a distinction between those. So I'm going to call that T2. Okay. And Newton's second law, I'm going to do this 0T2 plus 0, negative 19.62 is equal to 2 times 0, negative A. Again, you could call that positive A if you don't want to guess at the direction it's going to accelerate, and the sign will work out fine on its own. But this gives us our first useful equation that says T2 plus, I'm going to rearrange it a little, plus 2A is equal to 19.62. I'll call that equation 1. Now, free body diagram of equation 1. You have 9.81 down, T1 up. And so Newton's second law says 0 T1 plus 0 negative 9.81 is equal to the mass of 1 and then 0 positive A. So our second equation that we're going to hang on to says T1 minus A is equal to positive 9.81. Notice that at this point, we solved the problem in the case that the pulley was massless. We can't this time because those two tensions are different, so we have two equations for three variables. So we need some other stuff. So the first other thing that we're going to deal with is the rigid body kinetics of the pulley. Okay, so free body, well, let's just do now we're going to do the rigid body kinetics of the pulley. And we'll just go through the steps. So step 1, does this pulley have a fixed point? Yes, it's at the center of mass. So it's fixed at the center of mass. That's not usually the case. Usually if there's a fixed point, we're going to have to use the parallel axis theorem. But in this case, it's at the center of mass. So that means that our moment of inertia is, whatever I said before, 2.5 times 10 to the minus fourth. Okay. Now free body diagram. You have a force here. We don't know what that is. I'll just call that R. We already have an R. I fell for that trick last time. Let's call this F. Okay, that's not going to end up mattering to us. Well, I guess you always also have the weight of the pulley. That is the mass of, what was it, 0.2 times 9.81, so 1.962. And then you have two forces from the cables. Over here you have T2. And over here you have T1. Everyone good on the free body diagram? And so now we'll go to the table, row, force, moment. That force F. Okay, so our about point has to be at the center of mass because that's the fixed point. So our row vector for F is at the about point, so this is 0. We got Fx, Fy, cross product is 0. Now the weight, the row vector for that is also 0. The force is 0, negative 1.962. Cross product is 0. And now the two cable forces, T2, the row vector there is, this is a vector from the about point to where the force is applied. So this is going to be the radius of the pulley in the negative x direction. And we have that as 0.05. So this is negative 0.050. Force is 0, negative T2. And so the moment is counterclockwise 0.05 T2. And then T1, that row vector is positive 0.05 in the x direction. The force is 0, negative T1. And so cross product is negative 0.05 T1. Do we need Newton's second law for this one? No, there's a fixed point, so we don't need it, so we'll go straight to the moment equation. So we have 0.05 T2 minus 0.05 T1 is equal to the mass moment of inertia, 2.5 times 10 to the minus 4 times alpha. And that's our equation 3. Okay, we already have one more equation than we did last time, but we still can't solve it because we introduced this new variable alpha. But now what we have to recognize is, okay, so we have 3 equations for 4 variables, which means we need 1 constraint equation still. And what we're going to use is a relationship between the acceleration of those masses and the acceleration of the point on the pulley where the cable leaves, okay? And so what we're going to use is that the vertical acceleration of the point on the pulley where the cable leaves. That doesn't sound like a great wording, but I think you know what I mean, right? Anybody need me to clarify that? Is the same as the acceleration of the mass. Why did I specify the vertical acceleration? Why not just the full acceleration? Because notice that this thing, if it has any, hold on. Okay, if this thing has any angular velocity, then those 2 points here and here are going to have centripetal accelerations. But these 2 bodies don't have any centripetal, any horizontal acceleration. So I'm only worried about the vertical components of the accelerations. Okay? So how am I going to get the acceleration of the, okay, so here's the pulley. How am I going to calculate the acceleration of that point on the right? Yep. Yeah, and yeah, right. So if we, yeah, you're exactly right. I'm going to write down the full watermelon equation because that's always how you calculate acceleration. But we'd be throwing out the centripetal acceleration part anyways. So, you know, if this is the point, let's call this the point P, then the acceleration of P is going to be equal to alpha cross R plus omega cross R. This part is going to go away because it's horizontal. And so you just get A sub P is equal to zero alpha times R, so 0.05 alpha, and then 0 for z. And this has to be equal to 0, a, 0. So our fourth equation, let's make sure we got the signs right here. If alpha is counterclockwise, that point P is going to be accelerating up, which is how we assumed this is going to accelerate, so that looks good. Okay, so we have 0.05 alpha is equal to A. And now we have 4 equations for 4 variables, and we can solve this. Yes?
How do we get the angular acceleration in the y?
That was because alpha is 0, 0 alpha. R is 0.0500, and so the only non-zero component is 0 minus negative this.
Okay.
Whenever you have, when you're doing a cross product, any component that has zeros in both of those two vectors is going to be your only non-zero value of the cross product.
Okay.
Any other questions? Okay, well, I got to stop. But I'll give you a number for this on Wednesday, but it's not going to be a surprise, hopefully. What we're going to see is that there's going to be some reduction in acceleration compared to the massless case. And I'm not sure how big that's going to be because we just sort of pulled those values out of thin air. But the bigger you make that moment of inertia, the more it's going to decrease the acceleration. Yes?
Is the exam next Monday?
Yes, it's on Monday. Here, consult these notes. Exam 2, Monday. Topics. It's not going to have this pulley stuff, and I'm not going to give you any homework on that until Wednesday. Or maybe I'll give it, I don't know. I'll think about it. But you won't have it over the weekend. So you should be ready for stuff with wheels and stuff rolling down inclines, but don't worry about the pulleys with mass for the exam. Any other questions? Okay, have a good weekend.